In the last lectures, we discussed a q-polynomial distance regular graph containing Delsarte clique C. And we assumed our graph gamma has Q-Racah type. And using Delsarte clique C and vertex X in C, we constructed the irreducible bold T module W. And it turns out that this T module W has a universal DAHA HQ head module structure. And on this module, the element T, the generators, T3 T naught plus T3 T naught inverse acts as the addition symmetrics of gamma, and T naught T1 plus T naught T1 inverse acts as the dual addition symmetrics with respect to C, and T1 T2 plus T1 T2 inverse acts as the dual addition symmetrics of gamma with respect to X. Now, actually, the lecture we did last time is the generic theory. Just Q-Racah type is very most general type of q-polynomial distance regular graph. Today, we discuss dual polar graphs as a concrete example of a q-polynomial distance regular graph having a Delsarte clique, and show how the dual polar graphs are related to a certain DAHA. Well, unfortunately, our universal DAHA is not well fit into our theory. I mean, using the module structure for universal DAHA, we cannot find any connection. We cannot find connection to the T module W of dual polar graphs. So we need to find a reasonable and well-suited the DAHA to get a connection. That is the certain type of degenerated DAHA. So we will see how the degenerate DAHA appears in our story. All right. So first, we just review some properties of dual polar graphs. So Q is a prime power, and FQ is a finite field with Q elements. Let V denote one of the following vector spaces over FQ equipped with a non-degenerated bilinear form, as you see there in the table. And a subspace of V is called isotropic whenever our bilinear form vanishes completely on this subspace. And here's the fact. Each maximal isotropic subspace has dimension. So using this fact, we define a graph gamma as follows. So our vertex X is the collection of all maximum isotropic subspaces. Two maximal isotropic subspaces, say Y and Z, adjacent if and only if the dimension of the intersection of Y and Z is D minus 1. So the distance between Y and Z is I if and only if the dimension of the intersection of Y and Z is D minus I. And this graph gamma is actually distance regular with the diameter D. And we call this dual polar graph. So for the rest of this lecture, we fix a dual polar graph and some algebraic property of gamma. So intersection numbers of gamma, AI, BI, CI, where AI is Q to the E power minus 1 times bracket I1, and BI is Q to the I plus E power times bracket D minus I choose 1, and CI is bracket I choose 1, where bracket N choose I means the Q to the N minus 1 all over Q minus 1. And also, it's well known that the eigenvalues of dual polar graphs are this, theta I. Gamma has a q-polynomial structure with the ordering, a q-polynomial ordering, theta naught, theta 1 through theta D. And the dual eigenvalues of gamma are given here. So you see this. So some constant plus some constant times q to the minus I. The nice thing for dual polar graph is actually regular near polygon, which means it satisfies two conditions. First, there are no induced subgraphs of shape K1 to 1. So this shape. By this condition, each edge in this graph lies in a unique clique. Next condition, for vertex X and maximal clique C, with the distance X and C is less than strictly less than D, then there is a unique vertex in C nearest to X. Okay, so let's C be a maximal clique in C. Then by our comments, the size of C is actually intersection number A1 plus 2. But we know what A1 is. That is actually q to the E plus 1, which is exactly equal to the Hoffman bound or Delsarte bound 1 minus theta naught over theta D. Maximal clique in gamma is actually Delsarte. So we fix a Delsarte clique C in gamma. Now we fix a vertex X in C. And this is, we already know, just, theory of total legal algebra. So that A, adjacent symmetrics, and EI, the primitive idempotent, and A star, actually A star of X, the dual adjacent symmetrics, and EI star, dual primitive idempotent with respect to X. So we define the total legal algebra with respect to X. Primary T module with respect to X, mx hat. Then this primary T module, as we saw earlier, it has dual the endpoint 0, dual endpoint 0, and diameter D. So this element acts on mx hat as a Leonard system, and this is the primary Leonard system. And also we recall the distance partition with respect to Delsarte clique C. So we saw many times these distance partitions. So Ci is equatable in X. And also we define alpha ai tilde, bi tilde, ci tilde, the neighbor of Z in Ci. Numbers ai tilde, bi tilde, ci tilde, actually independent of Z. Actually, we discussed this fact in lecture 1. In fact, Ci tilde is equal to Ci, the original intersection number Ci, and Bi tilde is equal to Bi plus 1. Because we already found the general formula for Ci tilde, Bi tilde, involving Ci, Bi together with Ni formula, where Ni is just a number of vertices in C, the distance I from the vertex Z in the ith cell C, Ci. But our graph, dual polar graph, is near polygon, so Ni is 1. So we have the result. And we know the formula for Ci and Bi plus 1. Also, A tilde I, Ai tilde, Bi tilde, Ci tilde is constant raw sum, valence K. So we also obtain the formula for Ai tilde, Bi tilde, Ci tilde in terms of Q and E and D. So we recall the A star tilde, dual adjacency matrix with respect to C, and EI star tilde, dual primitive idempotent with respect to C. And in lecture 1, we proved that A star tilde is the linear combination of EI star tilde with coefficient theta I star tilde, which is given by here, you see this. But we know what the number Ni and the size of C. So that is just 1 over 1 plus Q to the E times theta I star plus Q to the E over 1 plus Q to the E times theta I plus 1 star. And also we know the formula for theta I star. So simplifying this quantity, then we got this expression. So again, theta I star tilde is expressed as the some scalar plus some scalar times Q to the minus I power. And of course, we can define the total legal algebra with respect to C, and also a primary T tilde module, MC hat. Everything actually we already discussed in lecture 1 and lecture 2. So again, we construct the two-dimensional distance partitions with respect to X and with respect to C, staircase shape. But the one thing we need to be aware of this picture is there's no connection between this cell and this cell. So if you choose this cell, for example, this cell is adjacent to this one and this one and this one. No connection between this. And now we choose a vertex from the cell Ci minus or Ci plus, and we count how many neighbors are there for each adjacent cell. So we routinely find the number of neighbors of Z in Ci minus and Ci plus. So this table explains everything for the neighbors of Z. So this partition is equitable, and by computing the number of edges between two cells, we can precisely find the size of every cell. So Ci minus and Ci plus is given by this formula. From this formula, we can say that each of Ci plus minus is non-empty. So everything is the special case of the Q-Racah case. And the subspace W, let V denote the C vector space consisting of column vectors indexed by X. And we view this V as a left mat C module. And we define W subspace spanned by the characteristic vectors of every cell in the staircase partition. And these characteristic vectors form an orthogonal basis for W. And we describe the action of A star tilde on this subspace W. So the action of A on Ci plus minus hat is given as follows. So first, A applied to Ci minus is the linear combo of these 4 terms, not 5 terms, because there's no the edge between these two. That's the difference from the Q-Racah case. Also, when we apply the A to Ci plus, then it is given by the 4-term linear combination. Now, the action of A star on W is just the eigenvalue of A star. So when we apply A star to Ci minus hat and Ci plus hat, this is just a dual eigenvalue theta I star. So in other words, this horizontal bubble, as we see earlier, this is the eigenspace of A star corresponding to the eigenvalue theta I star. So I just expressed theta I star as alpha star plus beta star times q to the minus I power. So where alpha star is this quantity and beta star is this quantity. So A star tilde acts on Ci plus minus diagonalizably. So this alpha star plus beta tilde q to the minus I power, that is actually the dual eigenvalue with respect to the Delsarte clique C, the theta I star tilde. This vertical the bubble stands for the eigenspace of A star tilde corresponding to the eigenvalue theta I star tilde. Right. So we just saw A acts adjacently on W, but 4-term recurrence, and A star and A star tilde act diagonally on W. And we recall the algebra, the T generated by Tabular algebra T and T tilde. Definition: A star tilde generate the bold T. So W is actually T module. Further, the T module W is irreducible, and we call this the primary bold T module. Now, our bold T module, primary module W, is actually module for both Tabular algebras T and T tilde. So we have 2 decomposition, mx hat perp, and mc hat perp. So that is just an orthogonal direct sum of irreducible T modules and orthogonal direct sum of irreducible T modules. So in Q-Racah case, we discussed the Leonard system on each summand, and each Leonard system has Q-Racah type because our Q-polynomial distance regular graph is Q-Racah type. But in our case, in this situation, dual polar graph, each summand has a Leonard system of dual q-Krawtchouk type. So, we will discuss these 4 Leonard systems and their parameter arrays. But before discussing that, we just recall the Leonard system of dual q-Krawtchouk type. So let phi denote a Leonard system on V. And let's consider the corresponding parameter array, P of phi, theta I, theta star, var phi I, and phi I. Then we say the phi has dual q-Krawtchouk type. Whenever there exist the scalars alpha, alpha star, beta, beta star, gamma, such that our parameter arrays are expressed in terms of alpha, alpha star, beta, beta star, gamma, and q, as you see here. We call this dual q-Krawtchouk type because, as we discussed in lecture 1, using this parameter array, we can construct the sequence of orthogonal polynomials, say ui, and when we evaluate this ui at the eigenvalue theta j, then this polynomial forms a dual q-Krawtchouk polynomials in the terminating branch of ASCII scheme. And because these 5 parameters, alpha, alpha star, etc., determines these parameter arrays, so we call this sequence parameter sequence of phi. But this form is quite different from what we have seen in Q-Racah case, because in Q-Racah type, we expressed all parameter arrays in terms of the so-called Leonard parameters, H, T star, R1, R2, etc. So to get such expression, you just replace alpha, beta, gamma, alpha star, beta star using this equation. Then we get the dual Krawtchouk type in terms of this parameter H, star, and so on. And also, I give one remark. So actually, dual Krawtchouk type is the limiting case of a Q-Racah type. So to get dual q-Krawtchouk type, you just take the R1, R2, and S star 0 in Q-Racah case. Then this special case derive the dual Krawtchouk case. In fact, when we have the Q-Racah polynomials, this limiting case, R1, R2, and S star letting to 0, then the Q-Racah polynomial becomes the dual q-Krawtchouk polynomial. So now back to our situation. So let us view our W as T module, and we recall the T submodule mx hat. Then this element acts on mx hat as a Leonard system. Because we have a Leonard system, it's very natural to think of the phi standard basis. The phi standard basis for mx hat is given, you see here. So using this basis, we think of the action of A and A star. Then the action of A is the 3-term recurrence, and A star acts diagonally. And this coefficient, the vi minus 1 and vi plus 1, that is actually intersection number of the Leonard system phi. Using this, actually find all parameter arrays in terms of alpha, beta, and gamma. So it turns out that our Leonard system phi has dual q. Everything is, the rest of the 3 summand are similar. So we think of the orthogonal complement mx hat per. Then this is T submodule. We obtain the Leonard system. So we naturally think of the phi perp standard basis, which is given by this. Because we have a standard basis, so action of A and A star on this basis gives the 3-term recurrence and diagonal action. And these coefficients, three coefficients, C, BI minus 1 perp, AI perp, and CI plus 1 perp intersection numbers. Using this data, comparing with the original intersection number of phi, we describe all these parameters. Turns out that P perp also has dual q-Krawtchouk type. Same thing, just that, the MC hat has dual q-Krawtchouk type, the parameter arrays, and also MC hat perp has the Lambda system having dual q-Krawtchouk type. So actually, earlier, our primary P module, we have four summand here, and we actually obtained all Lambda system for summand, and also describe the parameter arrays. It turns out that every Lambda system on each summand is dual q-Krawtchouk type. And then let me just display all parameter sequence for each Lambda system. If sigma is the parameter sequence of Lambda system phi, and we denote sigma perp, sigma tilde perp, the parameter sequence of phi perp, phi tilde, and phi tilde perp respectively, then each parameter sequence is given, you see here. This explains how our four summand are related to each other in terms of a parameter sequence. L per tilde perp is equal to alpha. L per tilde perp is L per star tilde perp is equal to alpha star, and so on. And this one is actually beta star. Also, we can define the projection map. So we define P, the orthogonal projection from W onto the T submodule MX hat. Then this linear map commutes with A and A star, the generator of the topological algebra. And by construction of the standard basis for MX hat and MX hat perp, we have these equations. So solving, now we just apply the P, the projection to both sides, and this equation. Then we have this equation as well that shows us the action of P on the space W. Similarly, P tilde perp, that is the projection onto MC hat. So we have the action of P tilde on CI plus minus. This is just nothing new, just a special case of the Racah case, but everything can be realized using the combinatorially, because dual polar graph is very nice combinatorial property, highly regular. And I just introduced the 5 bases, likewise the Racah case. The script C is the characteristic vectors for staircase fashion, and script B is the basis consisting of the standard basis, phi standard basis, and phi perp standard basis. And script B tilde is the phi tilde standard basis and phi perp tilde standard basis. And also we define 2 alternating ordered bases for W, B alt, B tilde alt. And I just showed some matrix representations of A star and A star tilde with respect to script C, and transition matrices between C, B alt, and B alt tilde. So first, this is actually a matrix representation of A on W. This is actually penti-diagonal matrix. Well, we can view this one as the block tri-diagonal matrix. So each block AI, BI, CI is given is this way. But matrix entry is very simple, comparing with Racah case. Dual polar case, everything can be described and determined by Q, D, and E. Matrix representation of A star is just a diagonal matrix because A star acts diagonally on W, and also A star tilde acts on W diagonally. So matrix representation of A star tilde is diagonal matrix. Some couple transition matrices So transition matrix from C to B alt is block diagonal matrix, 1 by 1, 2 by 2, 2 by 2, 2 by 2, and 1 by 1. And the reverse direction, transition matrix from B alt to C is just the inverse matrix of this. So transition matrix from script C to B alt tilde is the block diagonal, where each block matrix is 2 by 2. And the reverse direction is just nothing but the inverse matrix. So we described, we described the all matrix representation of A and A star tilde in the module bold T module W. Well, so as I mentioned, this part 1, let's say this is part 1, dual polar graph part, is nothing but the limiting case of the Q-Racah case. But still, I do emphasize this study is important because dual polar graph is very concrete example of the Q-Racah polynomial of the Q-polynomial distance regular graph having Q-Racah type, because there is no known example of the Q-polynomial distance regular graph having Q-Racah type containing Delsarte C. So our theory in lecture 1, 2, and 3 may remain, just the parameter and algebraic levels, but this dual polar graph really, realized combinatorial way. Okay, we think of the counterpart of the dual polar graph in algebraic version. That is the nil-DAHA of type C1 check C1. So here is some story why we focus on this nil-DAHA. Well, so when I finished the work, the relationship between Q-Racah Q-polynomial distance regular graph having Q-Racah type and universal DAHA of C1 check C1. Now I just turn my attention to the concrete example like a dual polar graph, but it was very difficult to find some DAHA which corresponds to the dual polar graphs. So when I was in the Tohoku University, Hajime Tanaka and I tried to find such algebra, but that time we realized that the Cherednik and Orr introduced certain degenerate DAHA, so-called the nil-DAHA, in 2012. So I just contacted Daniel Orr and asked about the nil-DAHA, and he gave some explanation how we construct the nil-DAHA. So thanks to his comments, Hajime and I finally find such algebra, the nil-DAHA of type C1 check C1. So here is the definition. So we fix the non-zero scalar k and k prime. Find the C associative C algebra H bar defined by generators and relations. And generators, five generators, t plus minus 1, u, x plus minus 1. And relations you see there. And where t prime is x times t inverse and u prime is x inverse times u plus 1, where 1 is the unity in this algebra. Actually, this definition is nothing but the specialization of the ordinary DAHA. So I will show how I get this, how I specialize the ordinary DAHA to get this nil-DAHA shortly. With this nil-DAHA, we set k and k prime with this scalar q to the minus e over 2, and k prime is there. And our goal is to construct a 2D dimensional module for H bar. So mimicking the idea of the Q-Racah case, we define the suitable, the block 2 by 2 and 1 by 1 matrices. Ti is some n 2 by 2 with a 0 entry here. Ui prime is 2 by 2, all 0 entry but this entry. And T prime I is 2 by 2 matrix, and T prime 0, 1 by 1, T prime D is 1 by 1. And also UI is 2 by 2 with non-zero entries here and here, and row 2 is all 0. And U0 is 1 by 1, but 0 matrix, and UD is just a negative 1. So using these block matrices, we define the bigger matrix. But before that, let's look at these properties of each block matrix. We have the following 1 and 2. So first, Ti minus K times Ti plus K inverse is 0 for every I 0 to D minus. T prime I minus K prime times T prime I plus K prime inverse is 0 for every I 0 to D. So this is just a straightforward. We can routinely find this property 1 and 2 using the 2 by 2 block matrix, 1 by 1 matrix. And also using defining that 2 by 2 and 1 by 1 block matrices UI and UI prime, we routinely find UI times UI plus 1 is 0, U prime I squared is 0. Now we define the 2D by 2D block diagonal matrices. This should be the bold lowercase t, T prime, U, and U prime by this. So we're familiar with this matrix representation because we discussed this a lot yesterday. And we define the lowercase bold x, T prime T. Then actually there is a representation from nil-DAHA H to the matrix algebra mat 2DC. That sense, T to T and T prime, and so on. With the 2D by 2D matrix, using those matrices, we can routinely check these 4 relations. By previous lemmas, we easily find this property, this 4 equation. Further, T prime, and X are invertible. This matrix, each of them has a determinant non-zero. Further, routinely we find that T prime is X T inverse. Also, X U prime is equal to U plus identity matrix. Everything is the straightforward. That means our matrix is T plus T minus U X plus X minus satisfy the defining relations for nil-DAHA. So we have this representation. We recall the T module W. We endow this module, the H bar module, into the W as follows. So T prime, U prime, and X, matrix representation of T prime, U prime, and X with respect to the basis Ci plus minus hat. So now we have the H bar module on W. In this module, we now discuss how our T action on W is related to this nil-DAHA case. So now we define the A star tilde, script A star, script A star tilde. As you see there, X inverse, tau, U prime, U, these are the generators of nil-DAHA. And for notational convenience, I define the scalar tau, this expression. Every I 0 to D minus 1, the actions of X and X inverse on the characteristic vector Ci minus is given as this linear combination you see there. So the idea is same as we discussed yesterday. So we routinely find this 4-term recurrence. And also, we can find the actions of X and X inverse on each characteristic vector Ci plus a hat. And each of them is given as the linear combination of the 4-term recurrence. So combining this action X and X inverse, we obtain the action of A on Ci plus minus. Now we have a five-term recurrence. So A Ci minus hat, A Ci plus hat is given by here, the linear combination with these following terms and with coefficient. Also, action of A and A star tilde on Ci plus minus hat is given by this these guys are eigenvectors of A star and A star tilde with eigenvalue this. So we almost done. So this is the result, main result on the degenerate case. So on W, we have these three equations. So A, adjacency matrix of the dual polar graph, acts as some affine transformation of the script A, and A star acts as A star, and A star tilde acts as A star tilde up to affine transformation, where this coefficient, these scalars are parameter sequence of phi and phi tilde. Further, the projection onto mx hat and mc hat acts as this element. The proof is, routine computation, just to find the matrix representation of this element and that element and compare with the matrix representation of P and P tilde, same as these three equations. And also because our T module W is irreducible, W is also irreducible H bar module. All right, so this is the main result. And now I just give several remarks about the nil-DAHA H bar. So to obtain the nil-DAHA H bar, we used, Hajime and I used this, the presentation of DAHA of type C1, check C1. So yesterday, I showed more nice presentation of DAHA of type C1, check C1, more symmetric. That is much better to work on our computation, but to obtain the nil version, nil-DAHA version, we use this presentation, but they actually same thing, same presentation. So anyway, I just recall the ordinary DAHA of type C1, check C1. So generators T naught plus minus, T1 plus minus, and X plus minus. And we have these relations where T naught prime is Q minus 1/2 X T naught inverse, and T1 prime is X inverse T1 inverse. Because this DAHA has 4 parameters together with the Q, now we specialize these parameters as follows. So we set T1 double dot is K1 times tau 1. T1 prime double dot is K1 T1 prime. Then T1 prime double dot is K1 T1 prime, but T1 prime by definition X inverse. And now because we have this relation, this is the definition of DAHA. So we replace T1 inverse by this and just plug in K1 into this parenthesis. We express T1 prime double dot as some expression involving T1 double dot. Next, we recall the relation tau 1 minus K1 times tau 1 plus K1 inverse equals 0. Now we apply K1 squared to both sides. Apply K1 for each linear factor. Then by our setting, K1 tau 1 is end up being T1 double dot, and this one also T1 double dot. Okay, so we also have we obtained these relations. Similarly, for these relations where I is 1, we apply K1 squared to both sides and simplify to get this equation. So by relations 1, 2, and 3, we can say that we just take the new generators for DAHA, 5 generators, T0 plus minus, X plus minus, and T1 double dot. So we have new generators. Now we specialize our parameters. K1 prime equals 1. We let K1, then the relations 1 to 3 we obtained becomes, as you see here. So K1 is 0, so this term will be gone. So we have this relation. And K1 is 0, so we got this. and K1 prime is 1, and K1 sends to 0, so we got this. So we have new relations by sending K1 to 0. So we now replace this expression to new notations like this. Then we obtain the presentation of a nil-DAHA. So this is called the double normalization. So we obtain the nil-DAHA by specializing this. But you may ask, what about other specialization? You know, of course we can make the bunch of degenerate case. For example, if we set a K1 prime by U inverse K1 for some non-zero scalar U, and then we just specialize K1 to 0, and our relation 3, this relation becomes this. Then this gives another version of nil-DAHA of type C1 check C1. And actually this representation is suitable for the irreducible Borda-T module for the Grassmann graphs. And that situation corresponds to the dual Q-Hahn. So I will show this nil-DAHA version tomorrow. But anyway, so we can make many the nil-DAHA from the ordinary DAHA. And I also give one more remark. In 2016, Majoko defined the 7 degenerate double affine Hecke algebras, and she discovered the connection between the theory of the pen-left differential equations and some families, the Q-ASCII scheme. So among the 7, one algebra called H type 3. That algebra is actually isomorphic to the nil-DAHA H bar we discussed today. Of course, I have no idea what about the other 6 algebras, 6 degenerate case. Are they related to, again, the distance regular graph side? I don't know, but anyway, that's a good observation. So let me end today's lecture.
Go backwards and go through the list of the Majoko variations of the DAHA and see if they correspond to any good q-polynomial, right?
So what slide?
So start with the Majoko. So she had the list of 7 variations of the DAHA.
Yes.
Can you start with any of those variations and go backwards and try to find the graph?
So actually, those 7 generated DAHA case correspond to Q-ASCII scheme. So each DAHA somehow related to the orthogonal polynomial, and that orthogonal polynomial actually form of the Q-ASCII scheme. I mean the infinite version. But what I can say is among the 7, only 2 type, H type 3 and H type 5, show the exact what type is. But that algebra is linked to the q-polynomial distance regular graph, the dual q-Krawtchouk type, and dual q-Hahn type Grassmann graph case. Other cases.
What happened with the just the ordinary Hamming graph? Simplest case, like hypercube, and there is a version of DAHA.
I think so. Yeah, I think so. So among the 7, there's the degenerate case when Q equals. I know that DAHA, but still, I'm working how to find the representation of that DAHA with Q equals 1. If we find some nice representation of that degenerate DAHA with Q equals 1, that might be linked to the theory of the Hamming graph case, but I don't know.
Well, included in Q equals 1, we got quite a bit more than just the Hamming graph. So, for example, any Racah level.
Oh, yes.
So this Q equals 1, I am in the list of Mazoka.
Yes.
Does that correspond to Racah or?
Frankly, I don't know what kind of a type is. But here is the one thing I can say. Recently, when Hong, I don't know how to pronounce. Yeah, Hong wrote a paper about the finite-dimensional representation of the Racah algebra and DAHA case, universal DAHA with Q equals 1. Maybe that algebra, some manipulating some, that algebra might be corresponding to one of the major course algebra, but that's my guessing. But
in his paper, in Howell's paper, does he talk about the Mazoka list?
I don't think so. He just showed the only nil version of he called that additive universal DAHA. So Q will disappear and the operator is given by the sum. Instead of the T naught, T1, T2, T3 equals Q to the negative 1/2, he's saying T naught plus T1 plus something. So additive. I hope that algebra might be one of the module course list, but I don't.
It sounds like something that should correspond to the Racah lemma as opposed to Q-Krawtchouk. So is it right that Cohen is using that algebra to analyze the Racah algebra?
Yes.
Okay,
Yes.
so that does sound like the Racah.
Yeah, Racah level.
Okay, let's thank you.